the only non-zero component is the corresponds to the age component. Whereas for L2 regularization, you put some small amount of weight on both components. Any questions? Okay, so just to recap on Lasso. So regularization is a modeling assumption, right? So we're saying we want to control for the complexity of our model class so that we don't overfit to finite training data. How do we control for the complexity of model class? Well, we can define a model class that's constrained in some way, which is equivalent to defining a regularization term that makes a penalty for a large W. How we define that penalty is a modeling assumption, right? Lasso uses a different penalty term than ridge regression. Lasso tends to incentivize sparse models. So unless you have an overwhelming amount of evidence from your training data, the weight vector you learn tends to have very few non-zero entries. Right? Ridge regression, on the other hand, says just that all the sum of the squares, the norm of the weight vector should be small. So it penalizes weights. If you want to learn a weight vector that has one really large weight and many small weights, ridge regression will not be good for that because it penalizes having such a large weight. It says in the absence of overwhelming amounts of evidence from the training data, I really don't want to see any weight vector with a single large weight. I prefer all the weights to be sort of homogeneous. So which one is better? Well, depends on your assumptions that you're making about the data. Right? If you don't with either one, you're implicitly making some assumption. In terms of predictive accuracy, in practice, ridge regression is often a bit more accurate. Sometimes a little, sometimes a lot. Than Lasso. Sometimes the difference in accuracy is irrelevant if you want efficiency. And sometimes sometimes Lasso is actually more accurate. And sometimes people want to use Lasso because they're trying to do sort of scientific analysis of the data, and they want to just recover the few non-zero components that really make a big difference in the prediction, and just to analyze them from a sort of more scientific or analytical point of view. And prediction is not the main goal. One thing that people often do is they run Lasso to recover the non-zero entries, right? The non-zero components, and then they rerun least squares regression on the dimensions selected by Lasso, and that tends to have fairly high accuracy. And this is sort of a very popular thing that people do in practice. So they don't use Lasso to learn the final model, they use Lasso for feature selection, and then they train another model on the selected features. I already mentioned this point, Lasso tends to give you sparse models, therefore it's easier to inspect the model to understand what the model is doing. Lasso, okay, so this depends. So Lasso is conceptually harder to optimize because it's not differentiable. On the other hand, because the number of non-zero entries tends to be very small, if you know how to optimize Lasso, it's actually very fast. And we'll cover this in a future recitation, although it's largely beyond the scope of this course. So just to recap regularization, we have L2, L1, multitask, and of course, you can insert your favorite regularization task here. Maybe you have some form of prior knowledge, right? For example, a simple formulation of regularization is, I have some W, right, that I know is good, then I want to regularize my W not to be close to the zero vector, but I regularize my W close to some other non-zero vector. Right? So that's one way of incorporating prior knowledge. You can also incorporate prior knowledge by not having uniform weighting on all the dimensions, right? This is equivalent to a uniform weighting of lambda on the square penalty of every dimension. If you think some dimensions are more important than others, you could put non-uniform penalties, right? So you don't have to use just these, although these are fairly the standard ones to do. Okay, so next week we'll be covering decision trees, bagging, random forests, boosting, ensemble methods. So these are all methods that are mostly inspired by decision trees, which is a dramatic departure from linear model classes. And will be very useful, by the way, for the Kaggle Mini project because it gives you very accurate predictors. And a recitation of probability statistics. Okay, that's it.